Happy Trade Center Eve, and we're live.
Trade deadline. Hey, recall when I told you what energy was, I said that energy was the ability to do what? Work. That's how we relate work and energy. It's the ability to do work. And I've given you two definitions of work. The first was an equation. I said that work was equal to what times what? Okay? But technically, that only works, no pun intended, that work only works if you have a constant force I gave you another definition of work. The second definition of work was if you had a force versus distance graph where maybe the force was increasing. We said that area was the force required to move it from that distance. I guess we can call this point A, point B. That would be the work required to move from A to B if we had a force versus distance or displacement graph. That actually becomes important next year when we start looking at rocket science, because we have to use that to figure out how much energy, how much work it takes to put a satellite in orbit. And you find the answer is an awful lot. It's about $10,000 a pound, give or take. It's pricey. So, for example, the guitar that Chris Hadfield brought on board the International Space Station probably weighs about 5 pounds, times about $50,000 to do that. I think a worthwhile investment, but still. There's a third definition of work. Oh, by the way, you know how I know to use the first definition? Because there's a force and a distance in the question. You know how I know to use the second definition? Because there's a picture of a graph. And this is for a reason, because this is the process of elimination, Margareta, we're going to go through. The work energy theorem, the third definition of work, says this. Work is equal to the change in potential energy plus the change in kinetic energy. That's really the work done on an object. If you want to find out how much work was done on an object, whatever potential energy it gained or lost, plus whatever kinetic energy it gained or lost, that's how much work was done. That's our third definition of work. When do I use that? If I don't see a graph and if I don't see a force or a distance mentioned. Like question number 6 from the homework from last day. Oops. You know what? Like example 1. A cyclist weighs 65 kilograms. His bike weighs 7.2 kilograms. So you know what? The total mass is, can someone go 65 plus 7.2 either in their head or on their calculator? Preferably in their head. 72.2? Yep. Okay, so our total mass here is 72.2 kilograms. Kyle, what does this question want me to find? How much what? Work. Okay. For him to what? What does A say?
Increases speed from rest. 5 meters per second.
To increase his speed from rest to 5 meters per second. Okay, work is force times distance. Do you see a force in newtons anywhere in this question? No. Do you see a distance in meters anywhere in this question? So that was my first thought, Emma. I scratched that one off. Oh, work is also the area under a force versus distance graph. My third definition of work, the new one today, the work energy theorem. Work is equal to change in potential plus change in kinetic. And by change in potential, that means you're either storing energy, like in a rubber band or in a bow and arrow or something like that, or you're changing your height due to gravitational. Reading this question, do you see any change in height mentioned? Okay, so I'm going to make a little note here. I think we're traveling horizontally, so change in PE is 0. And you know what? Anytime we're talking about a car or a bike or a change in speed, unless they specifically mention a hill, let's assume we're on flat level ground, Jake. We'll go simplest case. In other words, in fact, Dane, some textbooks actually say that the work energy theorem is just the change in kinetic energy. That's technically wrong. That's the work energy theorem as long as you're on horizontal level ground. I'm giving you the more universal one. Hey, what's change in anything? This is going to be final minus initial. This is going to be a half mv final squared minus a half mv initial squared. Do I know the mass? Yep. Do I know v final? Yep. Do I know v initial? Yep. By the way, does the mass cancel here? Is there a mass in everything? Careful. No, not in work. In fact, I think the more mass, the more work it takes, which is true. A heavier biker has to burn off more energy. This is why if any of you have like younger brothers or sisters that are like 5 or 6, or if you have nieces or nephews, or you babysit, the reason little kids can go forever, smaller mass, they don't burn as much energy as we do. They don't. It's far more tiring for us to keep up with a little kid. We're burning way more joules of energy. And it just gets worse for the rest of your life. Sorry. Oh, you know what? I think in this case, yeah? Why? What's my initial? Rest. So how much work does it take for this biker to go from 0 to 5? A half times 72.2 times 5 squared. Which is what? Shaq, what'd you get? I heard 900. 0.5. Oh, I didn't. Okay, joules. Yeah. So 902.5 joules. By the way, technically I should go to 2 sig figs, so I'll say 9.0 times 10 to the second joule. But yeah, 905 joules. 902.5 joules. By the way, by how much did he increase his speed? By how many meters per second? Not meant to be a trick question. By how many meters per second did he increase his speed by? 5 meters per second. Okay. B. Darian, what does he want to increase his speed from in part B? Now, how much of an increase is that? 5. People that don't have a physics background might say, oh, the answer is going to be 902.5. Turns out it's not. And this is going to explain a lot of sports events or exercise events to you. We want to find work. Well, work is force times distance. I don't have a force or a distance. Work is the area underneath a force versus distance. No graph. Work is going to be change in potential plus change in kinetic. Darian, I think I can safely cross out the change in potential. I think we're accelerating over flat level ground. Darian, what's change in anything? This is again going to be, and it's going to seem repetitive, but that's okay. I want it to be a bit repetitive. In fact, the amount of work to go from 5 to 10 is going to be a half mv final squared minus a half mv initial squared. It's going to be a half m 72.2 V final 10 squared minus a half M V initial squared. I don't think, even though it's the same 5 meter per second increase, I don't think you get 902.5. I see Manny type. Manny, what do you get? You're typing away on your calculator. I think you get something way bigger. Hang on, can I do this in my head? I think you're going to get 2,707.5? I cheated. 2,707.5. Way more. Halen, this explains, if you ride a bike? You've ridden a bike before. This explains why going from start to medium speed is nowhere near as tiring as going from medium speed to way faster speed. Even though the increase in terms of meters per second might be the same, you cannot keep up that maximum speed for anywhere near as long a time as you could the medium speed. What, by the way, what in this equation is causing that? Can you see it? Yeah.
It's because the half M V initial squared doesn't cancel out.
It's the squared. It's the squared that's doing it. You see, it's not even that it's not canceling out because, hey, let's look at increasing his speed from 10 to 15. Let's not walk through all the work, no pun intended. Let's just go straight to, it's going to be a half M V final squared minus a half M V initial squared. To go from still a 5 meter per second increase, it's not going to be 2,707.5 either. It's going to be a half Can I do this one in my head? Maybe. 8,100. 22.5? 8,122.5? Double check me. No, I think I'm way off, actually. I'm way off. Am I way off? Never mind, I'm using the wrong conversion factor. It's 3 times bigger to go from 0 to 5 than 5 to 10, but it's not 3 times bigger. It's going to be 9 times, I think, or 8 times. You know what? I got to crunch the numbers. By the way, what's making the difference here, Jake, is the squareds. That's what makes this not a nice linear relationship. That's what makes it, as the numbers get bigger, the amount of energy to do the same increase gets exponentially squared, bigger. Way bigger. This is going to be a half 72.2 times 15 squared minus 0.5 72.2 times 10 squared. 4,512.5. Is that right? Yes, because I should have been going back to 0, Mr. Dueck. Good gosh. Joules. I was tripling B. I should have been multiplying. Yeah. A. There's a mathematical pattern if you're really, really clever. Alex, is Joanne going to make it? Yeah? You sure? A little worried there, my friend. Again, Trish, I want you to notice, same increase, 5 meters per second, way more work. By the way, this also explains why, if you've ever been in a car, you can't just hold the gas pedal down and keep going faster and faster and faster and faster and faster and faster. I don't know if you've ever asked yourself why you can't, because the engine's still there. Isn't there an energy source still there? Yeah, there is. But as you go faster, it takes more energy to do a small increase. This is also why people will tell you, don't speed if you want to get good gas mileage. Slowing down doesn't just double your gas mileage, it makes a huge difference. Huge difference. Or if I want to go negative, that squared there explains why, well, the difference between getting into a car accident at 80 kilometers per hour and 20 kilometers per hour, what's 80 divided by 20? 4. It's not 4 times more damage, it's squared. It's 16 times more damage if you're in the 80 kilometer per hour accident compared to getting into an accident at 20 kilometers per hour. 16 times more damage because there's 16 times more energy, and it's got to go somewhere. It's going to go into you. Example 2. A model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Okay. Anthony, what's this question asking me to find? Okay, well, work is force times distance. I do see a distance. See it? Do you see a force in newtons? Okay. What's this question asking me to find? Okay, it's also the area underneath a force versus distance. Forget it. No graph. Oh, what's our third definition of work? The work energy theorem, which I think I did put on your formula sheet. Did I not? I hope. Double check someone for me, because it didn't used to be on there, but I think I put it on there. I did? Yeah. What's the work energy theorem? What's our third definition of work? Change in potential, assuming there's either some change in height or some stored energy. Read the question. Is there a change in height? Yeah. Okay, so I can't cross that out. Change in kinetic means there's some kind of a change in speed. Read the question. Is there some kind of speed thing going on there? Okay, I can't cross that out. What's change in anything? So now, how much work was done on the rocket by the engine? It's going to be potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. If you want to, Jake, you can kind of mentally put brackets there. The brackets don't make a difference in terms of mathematics, but if you want to put them there so you can see the first one is the change in potential and the second one is the change in kinetic, fine. I guess this is going to be mgh final minus mgh initial plus a half mv final squared minus a half mv initial squared. Is that okay? Are any of these 0? Which initial? Oh, we start out on the ground at rest, so you're saying I can cross that. In fact, I probably could have crossed it out on the previous line. Okay. Oh, we're starting out on the ground? Okay. So if you're designing this model rocket engine and you want to know in terms of the model rocket gunpowder, the fuel, how many joules of energy do I need to get out of this rocket engine? This is minimum, by the way, because we're ignoring air resistance, but it'd be close because rockets are pretty aerodynamic. Oh, I need to make sure that that chemical is able to give off, mass 0.15, 9.8. What's H final? 340 plus 0.5 times 0.15. What's V final? Squared. How many joules of energy does this rocket engine have to have minimum? Otherwise, this rocket ain't getting up that high that fast. Do you get that? I'll go 1,042 joules. Okay. 1,042 joules. Example 3. A car is traveling at 35 meters per second. Cool. Jake, what does A want me to find? How much what? You're right. Oh, force times do you see a force or a distance mentioned anywhere in the initial information? No. They do mention it in part B, but that doesn't help me right now. Oh, there's another definition of work. It's the area under a... Shut up, Mr. Dueck. No graph. Oh, okay. What's our new definition of work, Jake, my friend?
Work equals change of potential energy.
Is there any change in potential? Is this question talking about the car going up or down a hill or anything like that? So you know what? What's changed in anything? Can I go straight to the kinetic energy equation though? Can I actually go like this? It's going to be a half mv final squared minus a half mv initial squared. Is that okay, Dane? Hey, are any of those 0? Oh, coming to a stop. Okay. Well, so the amount of work is going to be negative 0.5 1250 times 35 squared. Am I going to get a positive or a negative answer? Now, this is not a direction. In fact, I'm going to ditch the negative in my final answer. What I am going to say is it has to, what it's telling you is this car has to lose energy. It loses energy. Otherwise, there's no way this car can come to a stop. Okay. What do you get? How many joules of energy must this car lose? A fair bit. That's why you don't want to get hit by a car, because you'll be absorbing that energy. Do you get 765,625 joules? What did I say? 765,625. Okay. B. Trevor, what's B asking me to find? Force. What did I just find in part A, Trevor, my friend? Is there an equation that has work and force in it? That'd be nice if there was. Oh, so you're saying now I can say, can you come out of there, Trevor, with a brand new equation? Can you write force as an equation from this? F equals what? The force required, the minimum force required to bring this car to a stop is going to be 765,625 divided by the distance, 82 meters. This is an average force. It might be bigger at some points. It might be smaller at some points. Do you get 9,337? 9337? Units. No, it's a force. By the way, If you had called this work negative, because we did get a negative answer on the previous one, what you're really saying with that negative is the force is acting in the opposite direction that the car is moving. The car is moving forwards, the force is acting backwards, which means you can get a vector out of it, because force is a vector. You can get a directional component out of it here. I'm not going to freak about that, but it's kind of nerdly cool. By the way, which force is it? What force is it that causes cars to stop? This is force of friction. McKinley, what's part C asking me to find?
The minimum coefficient of friction necessary for this to occur.
What's mu? I don't know. What's mu with you? It's asking me to find the coefficient of friction. What did I just figure out? Is there an equation that has force of friction and coefficient of friction in it? There is. Which one, Darian, my friend? I realized this was all one whole unit ago. It's on there. Force unit. You know this one because you said it a gazillion times. Friction equals mu times the normal force. I don't know the normal force. You know what? Up here to the right, I think I got room for a little free body diagram. There's my car. What are the forces acting on it? Get the obvious one. What else? Normal force pushing it up. Is this car speeding up or slowing down? So if it's traveling to the right and it's slowing down, there must be a force that way. Which force is that? Okay. So, Darian, you said friction is mu times the normal force. Look, another force same size as a normal force. Which one? Friction equals mu mg. McKinley, what was this question asking me to find? I don't know. What's mu with you? How would I get the mu by itself? Divide by mg. See, now we're putting a lot of stuff together. We're combining some work, energy, and we're pulling out some stuff from last unit. This is going to give us actually the ability to investigate car accidents. Mu is going to be friction divided by mg. It's going to be 7652. No, that's not right, Mr. Dueck. That's energy. It's going to be 9337, but I'll use the answer still stored in my calculator. Divided by 1250 times 9.8. This number divided by 1250 times 9.8. This pavement would require a minimum coefficient of friction of 0.76. 0.76 what? Units. Mu is no, it's just a ratio. It's actually, by the way, a force divided by a force. It's newtons divided by newtons. The newtons cancel. No units. 0.76, is that a high coefficient of friction or a low? That's pretty high. You'd feel good traction there. Okay. Let's investigate a car accident. An RCMP officer is investigating an accident. A car has struck a pedestrian at a school crosswalk. No witnesses. The officer measures the coefficient of friction at the accident site to be 0.65. They have a neat little device that measures it. It's a little springy, it's a little scale, it swings down, so they can get that. You can measure that from the pavement there. So we know mu. And there are skid marks that are 49 meters long, which means it took at least 49 meters for this car to come to a stop. Possibly more, because he might not have skidded the whole time, right? So this is minimum. Can we press charges? We need to find out if they're speeding. We need to find out if they're speeding. We need to take what we did in the previous question and sort of reverse the entire procedure. We're going to start out by asking how much work was involved here. We're going to start out by saying, you know what? And we've also turned the page. Better late than never, but better never late. You okay, Joanne? Yeah? Don't make me come back there. I'll stop the car and I'll make you walk. Is this question talking about hills at all, Jeff? No, you know what? I don't think there was a change in gravitational potential energy. And what's changing anything? What's changing anything? By the way, you want to memorize this if you haven't already. So you know what? If you don't know, you can write it right up here. Change in anything is always what? Final takeaway initial. Especially if any of you are taking physics or planning on taking physics 12 next year, I'll be asking you to find impulse, which is change in momentum, final minus initial. I'll be asking you to find the change in magnetic field, final minus initial. I'll be asking you to find the potential difference, which is change in voltage, final minus initial. You want to, as soon as you see a change in, it should be second nature. Oh, it's just final minus initial. I'm not going to freak out. But a lot of kids leave it blank because they can't remember what that symbol really means mathematically. So what's changing anything, Jeff, my friend? This is really a half mv final squared minus a half mv initial squared. I like this question. I like this question. I like this question. Hey, are any of these zero? Also, I like it because this is a nice application question. We're doing a little RCMP road science here. Are any of these zero? You know what? In any car accident, that's true. Your final kinetic has to be zero. I have yet to see any car accident where eventually the car didn't eventually come to a stop. Okay? Now, I'm going to get this. I'm ditching the negative in front of it because that negative is not directional. What it's saying is, I lost energy. Okay, I know that. But you'll notice I didn't drop the W down. What's another way that I can write work? Which force when you're stopping a car? Friction. What we want to do is we want to see if we should press charges. What that really means is we want to know, was the driver speeding? What do we want to find in this equation? VI. We want to get that by itself. How? How will I move that 1/2 over? You can either divide by 1/2 or timesing by 1/2 on this side is the same as multiplying by what on this side? 2, which is way nicer. I don't like a fraction inside of a fraction or anything. So if it's okay with you, I'm going to say, you know what? Put a 2 there. How would I deal with the m? Divide. And then how do I get rid of a squared? Okay, here is my car accident equation. The minimum speed, because this is assuming that all the skidding was stopping, but he might have stopped before skidding. Minimum speed this guy was traveling at is going to be the square root of 2 times the force of friction times distance divided by mass of the car. Oh, mass of the car you can get from the insurance, or they would probably have data tables of all the different car makes and models and the masses. You might need to take into account things like, oh, was the trunk full or not, other things, but okay. Friction is what times what? I don't know the normal force. Oh, I didn't draw a free body diagram. Maybe I should over here. Gravity down. You know what? It's the same free body diagram as we drew on the previous page. You know what the normal force is in this case, Dane? mg, right? So this is going to be, and I'm willing to bet, I don't know if any of you are going into the RC, any of you in the RCMP Academy or anything like that? So if any of you go into accident investigation, I would assume this is one of the equations you end up memorizing. It's going to be mu mg times the distance divided by m. Let's plug in numbers. The minimum speed when he started skidding, and again, Emma, remember this person could have slowed down before skidding, which means this would really give you a good argument in a court of law. To, what did I say the coefficient of friction was? 0.65. Mass of the car, what did I say the mass of the car was? Oh, wait a minute. Ha! I don't need the mass of the car, do I? Turns out, doesn't matter whether you're talking about a school bus or a little sports car. Keep going. G, oh, that I know. 9.8. D, how long did I say the skid marks were? I've scrolled down. What did I say? 40, 49? Oh, I don't need to divide by anything. Looks like the minimum speed is 2 times mu times g times d, square root of that. You know what? 25 meters per second. How do I go to kilometers per hour? Times by 3.6, so 25 meters per second times 3.6 kilometers per hour. How many kilometers per hour is that? Was this person speeding in the school zone? Okay. They're probably going to get charged with vehicular manslaughter or homicide if the person died. They're going to be facing serious jail time here, and there's not much you can do to argue with this one. Sorry, what was it? 90 divided, or not divided by, times 3.6. If they survived, you're going to get charged with reckless operation of a vehicle or speeding, and you'd get a significant speeding charge, not just a little bit over the speed limit. If the person did not survive, yeah, you'd be in trouble. By the way, going back to this equation here. Nope, never mind. I was going to come back to something, but I don't have it algebraically. I was trying to look at the relationship between coefficient of friction and distance. If I'd chosen to get the d by itself, the moral of the story is when it's raining, also, Jake, slow down. It's going to take you way, way longer to bleed off that kinetic energy. And if you're going twice as fast, it actually, because of that squared, takes 4 times more distance to bring you to a stop. If you're going 3 times as fast, because of the half mv squared, it takes you 9 times more distance to bring yourself to a stop. Be aware of that. Motorcycle video. Let's do some analysis here. Fortunately, this is a YouTube clip, so I got to pause the video for those of you who are watching at home. So, looking at the video, we saw this. We want to figure out how much work it took the motorcycle rider to bring himself, not to a stop, but to slow himself down, which is going to be change in potential plus change in kinetic. Although, did you see a hill anywhere in that video? I'm pretty sure that was on level ground, so I think we can safely say that. The amount of work is going to be a half mv final squared minus a half mv initial squared. We're going to need to do some unit conversion here. Okay? What was v initial in miles per hour? Do you remember? Okay, we saw 220 on the speedometer. Miles per hour. Well, I know that our freeway speed in kilometers per hour, not our highway speed, our freeway speed is what in kilometers per hour? A nice round number? 100. What's that in miles per hour down in the US? What's their freeway speed? 60. They're not quite the same, but close enough. So we can, I think, say this. If I put 60 miles per hour, that's the same as 100 kilometers per hour. So now I'm in kilometers per hour. If I go 220 times 100 divided by 60, how can I go from kilometers per hour to meters per second? So VI is how many meters per second? Can someone on your calculator go 220 times 100 divided by 60 divided by 3.6? I know that miles per hour is roughly twice as big as meters per second, so I'm expecting an answer around 100 or 110 meters per second-ish, give or take. I hope. Sorry? We're going to call that a nice approximate 100 meters per second. Okay? Now, V final was 100 miles per. By the way, when you're abbreviating miles, you have to put an I, because just an M by itself is what? Meters, and that's a very different unit of measure. Sorry. So miles per hour. And I guess, again, it's going to be times by 100, divide by 60, divide by 3.6. It should be somewhere around 48, 47, 45, 50 meters per second. Can someone crunch that for me? Oh, heck. Nice round number. I even thought about rounding it to 50, but we'll go 45-ish, give or take. Okay. So now we've got some numbers. We can, I think, figure out how much work, the amount of energy that the motorcycle, by the way, where'd the energy go? Has to go somewhere. Where did it go? What happens when you hit the brakes over and over and over and over and over and over and over again? You're heating up the brakes like crazy. It all goes into heat. A tiny amount of it goes into air resistance because he is bumping into the air molecules and giving them some kinetic energy. So, okay, some of it went into there, but the vast majority of it, you're heating up the brakes. So, a half, 345 squared minus a half, 300. 100 squared. You're going to get a negative answer because you're losing energy. We're going to ignore the negative. How much work was done slowing down? How many joules of energy? 1.2 million joules? A lot. I'll go, yeah, you know what? I'll go 1 point, because we've been very rough. 1.2 times 10 to the 1, 2, 3, 4, 5, 6. We'll ignore the negative. Joules of energy. Next question I'd like to answer is, how much power? What did we just find? Work. Is there an equation that has power and work in it? Oh, power is work over time. You know what? I think I can just look at the time stamp. Or you know what? Anybody got a stopwatch? We can just time it. If you got your timer on one of your phones, someone want to get out their timer on their smartphone. Give me a second here. Pause the video. So it looks like from the video, the time elapsed is, by the way, that's the abbreviation for is approximately equal to. It's instead of two parallel equal lines, you do squiggly lines saying, yeah, it's close to that. So this should be 1.2 times 10 to the 6th divided by 15. Divided by 15, and I'll just go times by -1 to get rid of the negative. And I get 79,750 watts. I get 79 kilowatts. Sorry? Yeah, if you use the 1.2 times 10 to the 6th. So let's call it 80,000. How long could this power a 60-watt light bulb? Well, power equals work over time. What's this question asking me to find? Time. Oh, get the t by itself. You know what? I think what I can do is I can times the t over to that side so it's on the top, and at the same time divide the p. I think I get this. Time equals work divided by power. It equals 1.2 times 10 to the 6th divided by you could power a bulb for 15 seconds. Big. Not crazy huge, but big. But wasted energy. Wasted energy. So what the Prius and other newer cars are starting to do is what's called regenerative braking. Instead of having the energy go into heat, when you hit the brakes, you instead actually turn a generator, and that bleeds the energy off and it recharges the batteries. Is that a hand up? Divided by 60. I'm sorry, that makes, this answer seemed way too small to me, and I was going, say what? Thank you, Valoria. Divided by 60. This makes way more sense. Now we're going to get a staggering answer. Something seemed wrong there, and my mind was bugging me. Thank you. 20,000 seconds. Or 330 minutes, or, yeah, a little over 5.5 hours. That makes way more sense to me. That's the number I was looking for. A lot of energy going to waste there. We can do better. It's wasted energy. So hopefully they'll start to find better ways to capture that. We're going to look at my Nerf dart gun next class. For now, if you want to, as a start, In theory, you can do number 1, number 2, number 3, and number 4, but don't hand them in because I'll pick up this lesson next class. We'll finish off the unit next class. I'll also probably have a take-home quiz for you. Then on Tuesday next week, great big review. Test next week, Friday.